Hello everyone and welcome in today's video. Today we are going to solve this U-shaped frame using the force method, and what is required from the task is to determine the support reactions at point A and at point B. Both point A and B are normal pins, and the flexural rigidity for all the members is assumed to be constant. The frames has the following dimensions A and B as shown here, and we have those bending moments applied at the fixed joints C and D. So without any further ado, let's start with the notes with the hand calculations. So as on the previous steps, the first thing to be done is to determine the degree of indeterminacy, and as at A and at B we have both pinned connections. There are going to be two actions acting on each of these supports. Therefore, this will leave us with four unknowns, and we know that there are three equilibrium equations for which if we do the difference, we are going to get one. And this shows the degree of indeterminacy of our structure. Next, let's apply the force method to solve this exercise. And to solve this exercise, one of the constraints at support B was released, the horizontal action. We set it to be free, as shown here, and we have case 0, and then we apply that virtual force on this direction from which we set the release, and we call it case 1. So now the structure is statically determinate, and we start to solve each of these cases and find the bending moment functions for the results which we get. So let's start with case 0, for which we have taken the bending moment at point A equal to 0, and we are able to find that the value of this support reaction is going to be 0. Then we take the sum of forces on Y equal to 0, and we define A0 as 0. Next we take sum of forces on X equal to 0, and A01 is going to be 0. And next thing to be done is to find the bending moment functions, and we start doing that by taking the cut sections on our frame where do we have discontinuities. So I started from the left side on the bottom part, and I take this cut section from here, and the bending moment is going to be 0. Same is going to be for the other side where we have the C0 support reactions, as the value of it was 0. Next, we continue to take the cut section on the other discontinuity and finding the bending moment function is equal to m for these boundaries bigger than 0 and smaller than b. Next, let's solve case 1, and the same principle applies here. We have to take sum of bending moments at point A equal to 0 to define the reaction at C1, which is going to be 0. Then we take sum of forces on Y, A1 is going to be 0 again. And by taking the sum of forces on X equal to 0, we define that A10 is going to be minus 1, meaning that it's going to have a different direction from the one which we supposed. Next, let's find the bending moment functions again as on the previous case, for which we have to find these bending moment functions where do we have discontinuities on our structure, and we find the first bending moment function for this discontinuity, which is going to be minus x. Next, we take another cut sections and we define this bending moment function m1 as minus a, and we define the bending moment function m1 for the discontinuity, which is going to be x. Here we have a summary of results for each of the cases. Case 0, these are going to be the bending moment functions with the given boundaries, and the same thing is valid for case 1. We have the given bending moment functions for these boundaries on our structure. Next, we apply the force method, and from the compatibility, we get that our unknown or our equation is going to look like this. And let's start to solve these two unknowns by using the integrals as shown here, and some of the integrals are going to cancel out as those bending moment functions as we calculated previously are going to be 0. We calculate the first unknown, and then we jump on calculating the second unknown as shown here, and this is going to be the value of it. Now, as we already have these two unknowns, we can find our unknown, which is going to be the horizontal reaction at support C, for which we released it when we solved it with the force method. And we go and find our unknown, and this is going to be the value of that horizontal support reaction at point C parametrically. So this is good way of solving the exercise, and we can utilize this result if in the future those dimensions or those bending moments at the corner joints are going to be changed. Next, by utilizing the force method again, now it's easy to determine the other support reactions for our structure as shown here, and we get this following value for the AX support. We get AY 0 and BY is going to be 0. So next, let's just assume some values for which we can solve. Then after that, we are going to compare the results with a finite element method software. So if we assume that those bending moments are going to be 20 kilonewton times meter, and we have A equal to 5 meter and B equal to 3 meters, these are going to be the following results which we have if we input those values in these formulas which we already calculated. We're going to have Bx is going to be 1.89 kilonewtons, Ax minus 1.89 kilonewtons, and AY and BY is going to be 0. Building the model in a finite elements software is going to give us the following results, and as you can see here, we have these values. This is going to be our point A, which is going to be AX value, and this is going to be point B with BX component as shown here. So this comes to prove that our hand calculations are correct. So this was the video for today. I really hope you enjoyed today's video. If there is any questions, please leave them down in the comment section below. Do not forget to like, share and subscribe. Thank you very much. See you on the next video.